Welcome back to Jesse Lauscher's Physics. Today we'll look at kinematics, which is the mathematical modelling of motion. A kinematics problem could ask how fast something travels, or its acceleration, or where it will be when, but it doesn't ask why. Arguably, kinematics is more math than science, and the physics really comes with the next unit of dynamics, when we ask why things move as they do. But since an understanding of kinematics is essential for dynamics, and in fact most of physics, especially AP Physics 1, it's how virtually all high school physics courses begin after introducing formalities like units and uncertainties. Before we look at kinematics, it's important to differentiate it from the physics most students have done before. Let's look at a typical junior high school problem and review what we've done on units so far. Xiaohe drives 5 kilometers from her home to school at an average velocity of 30 kilometers per hour. How long will it take her? Here's the formula from the AP equation sheet. The arrows above the x and v just mean that they're vectors, which we'll cover in another video. So, in other words, average velocity equals displacement over time, so time equals displacement over average velocity. Now we could either convert to SI units from the start or not. I don't think it really matters, as long as we're consistent. I'll keep it in kilometers and hours for now. The kilometers cancel, the h goes to the top, and we're left with 0.16667 hours. Now, many students would be tempted to note that the 6 is recurring, and it's fine to note that in your own working, but we must round our final answer to 2 significant digits. But since we wouldn't say 0.16 hours, I suggest converting it to 10 minutes. I think we could either leave it there or convert it to SI units of seconds, but most importantly we must round our final answer to 2 significant digits, the lowest number of significant digits given in the question. Since 10 could be either 1 or 2 significant digits, and 600 could be 1, 2 or 3 significant digits, I'll note that it's 2 for both. Also, although I tend to write min for minutes so that it's not confused with the unit metre or the quantity mass, since second is the SI unit we should write S and not SEC. We just calculated her average velocity, but what about her instantaneous velocity? In reality, the car must accelerate, then it might continue at constant velocity, although probably not in the real world with things like traffic lights, and then it must decelerate before Xiaohe can step out safely, or else she'd go flying through her windscreen when the car stops so suddenly. In most AP Physics problems, we do consider the acceleration, and one common mistake physics students make is to use velocity equals displacement over time to try to solve problems which involve acceleration and which don't ask for average velocity. By definition, acceleration is the change in velocity divided by the corresponding change in time, so its units are meters per second squared. Just as in junior high school we usually assume that velocity is constant or just calculate average velocity, in AP and most other high school physics courses which don't use calculus, we usually either assume that the acceleration is constant or just calculate the average acceleration. So it would be more accurate to analyse Xiaohe's motion in 3 parts. First her acceleration, then her travelling at constant velocity, and then her deceleration. Only the middle part could be calculated using the junior high school formula velocity equals displacement over time, while the other 2, because they involve acceleration, or deceleration, would require one of the equations of motion, which are given in the AP equation sheets, although you'll probably get to know them very well throughout the course of your physics study. When solving kinematics problems, it's important to choose the origin, that's the starting point, carefully. It's usually the point the object starts at, in which case x0 is 0, but if not, then x0 is the starting point, and that's why it appears in the equations of motion. As an example, let's say that Xiaohe decelerates from 30 kilometers per hour to rest at a rate of 2 meters per second squared, and we want to know how far she travels during this time. First, let's look at what we know. Her initial velocity is 30 kilometers per hour, her final velocity, rest, is 0, and her deceleration is 2 meters per second squared. Since it's deceleration, and because we assume her driving direction is positive, that is, we assume the velocity is positive, we assume that the acceleration is negative, but we'll look more at that when we get to vectors. Since we have time in hours and seconds, let's convert kilometers per hour to SI units, that's meters per second. If you're not sure how or why I'm doing this, you might want to watch my video 01 on quantities and units. It's worth remembering that to convert from kilometers per hour to meters per second, we divide by 3.6. So we need an equation which contains x, since that's what we need to calculate, and doesn't contain time. Occasionally no equation suits us perfectly, so we need to solve for one quantity and then use that to solve for another, and I'll go over one of these rare, difficult problems at the end of the video. But in this case, clearly the last equation is the one we want. In this case, as in most cases, at time t equals 0, she was at the origin, x equals 0, so x0 is 0. So we just plug in the numbers, rearrange it, and solve for x, which gives us a final displacement of 17.3611 metres. Finally, since the minimum number of significant digits given to us in the original question was 2, We should round our final answer to 2 significant digits. In kinematics, we start with one dimension, like in the previous problems, so we simplify motion to a straight line, such as show her driving her car along a straight road. We usually use x for displacement, that's distance with a direction, which we'll cover more when we look at vectors in another video. When we model motion in the vertical dimension, such as if we wanted to know how far a ball would have travelled at a given time if it were dropped off type A 101, then we can either turn our axes around so that x is now up-down, or we can use y instead of x to model vertical displacement and change our equations accordingly. Later, when we look at two-dimensional kinematics, such as projectile motion, we'll see that we usually use y for vertical displacement and x for horizontal displacement. None of this matters too much, as long as you're consistent and show what you're doing as you go. I really recommend drawing a quick diagram to make it clear to yourself and anyone else reading your work, such as your examiner, what each letter represents, and being consistent throughout your work unless you clearly state otherwise. Now, we wouldn't actually want to drop something off type A 101 because it would be incredibly dangerous, as even a falling coin can kill someone below, but falling objects make up an important part of most high school physics courses. We usually assume what we call idealized conditions, which unless stated otherwise means no drag or other forces act on the object besides gravity, so everything accelerates downwards at a rate of g, which is usually rounded to 9.8 meters per second squared. Our example before was actually a bad example, since a basketball has a lot of friction, and we'll look more at falling spheres in another video. One of the most common traps in freefall problems is vectors and directions. We must always choose which direction is positive and then be consistent with it. Some books always assign upwards as positive, but I encourage my students to choose whichever direction will make the calculations the simplest by avoiding negative numbers as much as possible. For example, let's replace the ball with a screwdriver, which will say a construction worker accidentally drops, and calculate how long it will take to reach the ground. In both cases, we'll use x for the vertical dimension, but we'll show how it works if we assign upwards as positive and downwards as positive. Let's start with downwards being positive. Now the acceleration and the displacement are both positive. Since we place the origin at the starting point, x0 is 0, and since it's dropped, its initial velocity is also 0. Time is what we want, and we don't need to worry about the final velocity. Clearly, the second equation has the variables we need. Since we usually place the origin at the starting point, it's often simplified to this, and in our case it's easier because v0 is 0, saving us from needing to solve a quadratic. Then we can just plug in the numbers and round our final answer to 2 significant digits, since that's how many significant digits we used for g. Since 10 can be either 1 or 2 significant digits, I suggest making a note of the number of significant digits in our final answer. But what if we had assigned upwards as positive instead? Now both the acceleration due to gravity and the displacement are negative, since it's moving and accelerating downwards. When we plug these into the equation, the negatives cancel each other out, giving us the same final answer. This is what we would expect, since however we choose to set up our model shouldn't affect the final answer, which should relate to the real world. Now let's say the second part of the question asks for the velocity of the screwdriver just before it hits the ground. Now this just before is a common and sometimes confusing term in physics. From the moment it hits the ground will provide an upwards force, which we'll look at in the next topic, and cause the screwdriver to decelerate, so its acceleration will no longer be 9.8 meters per second squared downwards. So we want to calculate the velocity in infinitesimally short amount of time before it hits the ground, but we assume that that amount of time is so small that we don't need to include it in our calculations. I've had some students try, for example, to calculate its velocity after it's fallen 507.999 meters, so that their value really is just before. This is very logical, but it's just not how it's done. So with problems like this, we should just use the given height, which in this case is 508 meters. Since velocity and acceleration are both downwards again, let's keep downwards as positive. I really encourage my students to make a note of this in their working. These values are the same as before. Now we have time from the last question, and we can use it if we need to. But since we calculated that value ourselves, it's less reliable than the other values which were given to us in the question. And we'll keep lots of significant digits to make our calculation as accurate as possible, and then round our final answer appropriately. Clearly the first formula would work, but it uses time. The last formula doesn't use time, so we'll use that one, even though it's slightly more complicated. So we substitute in the values, and it comes out an incredibly high velocity of 100 meters per second, rounded to 2 significant digits, since that's what we used for the acceleration due to gravity. But how about the plus and minus? We chose downwards to be positive, but if we'd chosen it the other way, we'd have had negatives here, and they would have cancelled each other out, giving us the same final answer. And in any case, we have a plus or minus sign here, so even if the answer for the velocity were negative, it would have been lost in the square root calculation. But this is physics, not math, so we just need to think about the physical situation. We know that the final velocity is downwards, so you might want to just look at your model and see that downwards is the positive direction and say that the answer is correct, being positive. Now, if you've shown you're working well, that might be okay, but since the problem is about the real world, so too should our answer be. And since we were asked to calculate the velocity, which needs a direction, as we'll look at more when we look at vectors, we should give our final answer with an actual real-world direction. So let's just say down or downwards, and that is our final answer. Now let's look at a slightly harder problem, which I'd say is about the upper level of AP and most other high school kinematics problems. It's from Giancoli, my favourite high school physics textbook. It's chapter 2, problem 49. A falling stone takes 0.31 seconds to travel past a window 2.2 metres tall. From what height above the top of the window did the stone fall? So, if we start our imaginary stopwatch as the stone passes the top of the window, then this is what we have. But the question asks for this x. Now, like in the last problem, we'll assume that downwards is positive, since this makes it simpler. But please note that some books and some teachers always use positive for upwards. Now, as always, let's look at what we know. The acceleration is due to gravity, and since we define downwards as positive, it's 9.8 metres per second squared. X is 2.2 metres and t is 0.31 seconds. But it's important to note these two values are assuming that the origin, or x0, is at the top of the window. But in order to calculate where it was dropped from, it's probably easiest to use a different origin. So we're essentially setting up two mathematical models here, the blue with its origin at the top of the window and the green with its origin at the drop point. Since it's the green model which can actually give us our answer, let's see what we have there first. Obviously, the acceleration is the same, we want x, and we don't care about t. And since it's dropped, we know that the green v0 is 0. So do we have a formula which can give us what we need? Unfortunately not, but this formula could if we had v, its velocity at the end of the time we're modelling in green. But that is the velocity at the beginning of the time modelled by the blue equations, so we might call it blue v0. And because in this blue model the stone is at the origin at t equals 0, blue x0 is also 0. Here's a more common simplified version of this formula, and then we can substitute, rearrange, and solve for v0. This gives us our final velocity in the green model, so now we can use this formula, commonly simplified to this, and as we said before, v0 is 0 because it's dropped from this point. Then we can substitute in our numbers, rearrange, and solve for x. The original question states values to two significant digits, so that's how we should round our final answer. So it looks like the stone was probably dropped from this window, not the one above. Finally, as I mentioned before, please don't drop things out of windows, as even just the speed shown here is high enough to do serious harm to anyone or anything it could hit below. Finally, let's look at a problem which really is at the upper limit of most high school physics courses, including AP. It's problem 43 from chapter 2, Halliday Resnick Walker, my favourite college and AP Physics C-level textbook. We'll just look at part A, but we may return to part B in a video on graphing motion. When a high-speed train travelling at 161 km per hour, which I'll say here is 44.7 metres per second, rounds a bend, the engineer is shocked to see that a locomotive has improperly entered the tracks from a siding and is a distance d equals 676 metres ahead. The locomotive is moving at 29 km per hour. I'll say now that's 8.06 metres per second. The engineer of the high-speed train immediately applies the brakes. What must the magnitude of the resulting constant deceleration if a collision is to be just avoided? Now, I'd really encourage you to pause the video, think about what the problem is asking, come up with your own model, and draw a diagram of it. So, what do we have here? The engineer driving the high-speed train, which from now on I'll just call the train, rounds a corner, and then she realises that the smaller train, called the locomotive in this problem, servicing the tracks, is moving at a constant velocity of 8.06 metres per second, unaware of the high-speed train approaching it from behind. So the engineer of the high-speed train jams on her brakes and slows down just enough to avoid a collision. Now, as with any model, our first step is to choose where the origin is and which direction is positive. Now, we could model the train and the locomotive separately with different origins, in a similar way to how we had two models in the last question, and then connect them at the end. But this time I'm going to use one mathematical model for both the train and the locomotive, and I'll set the origin at the location of the front of the train just as the engineer applies the brakes, because from this point until the end of the time we need to model, the train is decelerating at the rate we need to calculate. Let's see what we have for the train, which I'll show in orange text. The small subscript t just stands for train. x0t is 0, since we're modelling the front of the train, and it's at the origin we choose at time t equals 0. Its initial velocity is 44.7 metres per second, and its final velocity is 8.06 metres per second. Many students assume that the final velocity of the train must be 0, but it only needs to slow down to the same velocity as the locomotive, because from that time on it will be travelling slower than the locomotive, so it will be unable to collide with it. We need to calculate the train's acceleration. We're not told anything about its time or displacement, but in a problem of this level we often need to bring variables into our calculation even when they aren't stated in the question. Now let's look at the locomotive. It has a non-zero x0, since it starts 676 metres ahead of the point we chose for the origin. You could of course have chosen the origin to be where the locomotive is at the start of the time we model, and it would still work, perhaps even more efficiently. We'll model the back or the rear of the locomotive, since that's the part which would collide with the train if it were to. The locomotive has zero acceleration, so it doesn't really make sense to give it an initial velocity v0 or a final velocity v. It just has a constant velocity of 8.06 metres per second, which I'll call v locomotive, or vl. We're not told anything about time for it. So, what can we do with this information? The only equation we have to model something with displacement and constant velocity is the good old junior high school formula, velocity equals displacement over time. And since we're given velocity and displacement, we're definitely going to need to use time and displacement in our equations somewhere. And since we need them for the locomotive, we'll probably need them for the train as well. So we can model the deceleration of the train using equations of motion, the ones used in high school physics courses, and the constant velocity of the locomotive using good old junior high school v equals d over t. But where can we go from here? If the train decelerates at the minimum rate possible so that it doesn't quite collide with the locomotive, then just at the moment that the train's velocity reaches the same as the locomotive's, its front, which is the part we're modelling, will be at the same place and thus have the same displacement as the rear of the locomotive, and this will happen at a time we'll call t. So, mathematically, we can say xt equals xl. So, let's figure out the displacement of the train and the locomotive as a function of time. For the locomotive, its displacement is fairly easy to model. It starts 676 metres ahead of the origin, and then each second it moves a further 8.06 metres away. I suggest thinking about this intuitively, but if you'd like to use a formula, we could use this one, where the last part is 0 because its acceleration is 0. We can also use this formula for the train, but now x0 is 0 because we set the origin to be where the front of the train is at the start of the time we're modelling. That is, the moment the engineer applies the brakes. Substituting the numbers in, we get this. Now, since the displacement must be the same at time t, we can make these equations equal, giving us this. Now, it may look like we're almost there, but unfortunately, we have two unknowns, a and t, and only one equation, so this equation is unsolvable as it is. But all is not lost. When we get stuck at a point like this, it's a good idea to find a variable we haven't used and try to somehow bring it into the equation and use it to eliminate one or more of the unknowns. And we haven't used the final velocity of the train. Now, if we could eliminate time, then we could just solve this equation for acceleration, which is what the original question actually asks for. But since time appears 3 times and acceleration only once, it's probably easier to eliminate acceleration, even though we'll have to solve for it again at the end. So let's rearrange this formula, which is commonly simplified to this, to make acceleration the subject, and then insert it in here. That gives us this equation, which now only contains one unknown variable, time, which we can then simplify and solve for t. Then, finally, we just use the same equation, substitute in the value we just calculated for time, and solve it for acceleration. The acceleration is of course negative, because the train is decelerating, but because the original question asked for the magnitude of the deceleration, we should drop the negative. And, of course, we should round it to 3 significant digits, because that's how many are given in the original question. That gives us a magnitude and final answer of 0.993 metres per second squared. If you can solve the last 2 problems, then you should be able to solve virtually any kinematics problems in AP, IB, or other major high school physics courses around the world. As always, thanks for watching.